All right, physics students, I'm going to take you through the homework on work and energy, or kinetic energy and the work energy theorem here. I had some production problems here, and so I already did number 1 for you. And let me just read that. A tugboat pulls a ship with a constant net horizontal force of 5,000 newtons and causes the ship to move through a harbor. How much work is done on the ship if it moves a distance of 3 kilometers? Okay, so my force is 5 times 10 to the third, that's 5,000 newtons. It's pulling it straight here, so the direction of this force and the direction of the motion are the same, so the angle between them, theta, is 0. And this is 3 kilometers for the distance, which is the same thing as 3,000 meters. I don't know why that question mark's there. Okay, equals 3,000 meters. All right, so to find the total amount of work that it asks us to find, work equals force times distance times the cosine of theta. Now, if theta is 0, the cosine of 0 is 1, and we can just cancel this out. And most of the problems we do, it's just going to be force times distance, but there will be a few where you do need to know the angle. All right, so 5,000 newtons times 3,000 meters equals 1,500 joules. All right, then moving on to number 2. Number 2 said a weightlifter lifts a set of weights a vertical distance of 2 meters. If a constant net force of 350 newtons is exerted on the weights, what's the net work done on the weights? So here I have a distance of 2 meters. That's given in the problem. He lifts with a force of 350 newtons. And to find the work, we go work equals force times distance, right? Times the cosine of theta, but again, theta is 0, so we don't have to have it. So we go 350 newtons times 2 meters equals 700 joules. That's the answer for number 2. All right, this is where my video kind of cut out before. We have a shopper in a supermarket pushing a cart with a force of 35 newtons. Now, she's pushing down on the cart. She's not pushing it straight ahead. She's pushing down this way. That's my force, 35 newtons right there. Find the work done by the shopper on the cart as the shopper moves along a 50-meter length of aisle. So she's going to move a distance of 50 meters. Okay, so our work is what we're trying to find, and the equation for that is FD cosine theta. And now it's just plug and chug. So we go 35 newtons times 50 meters times a cosine of 25. And again, the reason we have that cosine in there is because we only want the x component of the force. So let me do this here. Can we see that? We go 35 times 50. I should probably turn it on first. 35 times 50 times the cosine of 25 equals 1,586 joules. All right, moving on to number 4. Number 4 says if 2.0 joules of work is done in raising a 180 gram apple, how far is it lifted? So it's asking us to find a distance here. We have an amount of work, which is 2 joules, and it says that the mass of the apple is 180 grams. All right, so why is it important for us to know the mass of the apple? Well, first of all, because if we know the mass of the apple, we know how much it weighs, right? And this is going to be 0.18 kilograms. And why do we want to know the weight? Well, remember, weight is the force. Our equation so far has been work equals force times distance, cosine theta, which again, here's my apple. This is why you should draw a picture. Here's the force of gravity pulling that apple down, but I'm lifting up with a given force. That'll be my applied force. And if it's moving at a constant velocity, these two forces are equal, all right? So if I know the weight of the apple, I know the applied force. So let's find that weight. F sub g equals mass times gravity equals 0.18 kilograms times 9.8 meters per second squared. So I'll pull this out. I'll go 0.18 times 9.8 equals 1.76. So it's 1.76 newtons. All right, so that's how much force the earth is pulling down. That's how much force I'm using to pull the apple up. All right, so if we want, again, the angle here, my force and my motion, there is no angle. So that's 0. The cosine of 0 is 1. Okay, so that cancels out. It doesn't cancel out the whole thing because it's 1. If it was 0, then it would cancel out everything, but it's not. So let's take this equation and solve for distance. And we get distance equals work over force. And that's going to be 2 joules divided by 1.76 newtons. And 2 divided by 1.76 equals 1.14 meters. All right, so that's the first part of this assignment. All right, so we're going to take a look at the second part of the assignment now, which is page 157, 1 through 3, 5, and 6. I am not going to go through all of these because they are, some of them aren't math problems. I will do the math problems. So number 3, a worker pushes a 1.5 times 10 to the third Newton crate with a horizontal force of 345 newtons, a distance of 24 meters. Assume the coefficient of kinetic friction between the crate and the floor is 0.220. A, how much work is done by the worker on the crate? B, how much work is done by the floor on the crate? And what is the net work done on the crate? So, first of all, let's draw a picture here. Here's my crate. It says that the crate has a weight of 1,500 newtons. Okay, that's F sub G. All right, and it gets pushed with a force of 345 newtons. That's going to be an applied force. There is some friction going backwards here, so we'll call that kinetic friction. We don't know what that is. And there's obviously going to be a normal force. Now, because it's on a flat surface, the normal force and the weight will be the same. Right, so that means this is 1,500 newtons. So I'm not going to have to worry too much about figuring out, what that is. All right, now the first question is, let me write down the coefficient of friction, 0.220. So question number 1, how much work is done by the worker on the crate? So the worker applies a force times a distance. Angle is 0 here the whole time, so I'm going to drop off the cosine theta part because that only applies if there's an angle between the force and the motion. So the worker pushes with 345 newtons, and the worker moves it, what was the distance? 24 meters. So 24 meters. Pull out my calculator here. And I go 345 times 24. I'll turn this on, how about? 345 times 24 equals 8,280 joules. Now, question B says, how much work does the floor do? All right, you might say, how can a floor do work? Well, it creates a force, right? So what force does the floor create? Friction. How much friction do we have? Friction equals the coefficient of kinetic friction times the normal force. That is an equation that we used in the last chapter. Coefficient of kinetic friction is 0.220. The normal force is 1,500 newtons. That's the weight of the crate. And so here we have 0.220 times 1,500, and I get 330 newtons. All right, so that's the force that the floor applies. So how much work does the floor do? The force of the floor, or Fk, times the distance that it travels, which is 24 again, times the cosine of theta. And you might say, well, wait a minute, isn't the direction of the force the same as the direction of the motion? No. The direction of the force is this way. the direction of the motion is this way. What's the angle between those two things? That's 180 degrees. All right, so if I go FD cosine theta, I go 330 newtons times the distance of 24 meters times the cosine of 180. And what's the cosine of 180? If you think about math, it's -1. So we're going to go 330 times 24 times the cosine of 180 equals -7,920 joules. That's how much work. So that's negative work. And then the last question is, what's the net work? Well, the net work that we do, the amount you have when you all is said and done and added together, is we take the work of the worker and we add it to the work of the floor. And that's going to be the work of the worker, 8280 minus 7920. And what is that? That's going to be 80 plus 280. That's 360 joules of work done on the crate. Right? So the worker has to supply a lot more work than that, but the friction of the floor is taking a lot of his work and therefore energy away, and he's only able to give the crate that much energy. All right, we're going to skip ahead. Page 160, number 1 through 5. All right, so number 1, again, I'm going to rifle through these pretty quick. Calculate the speed of an 8 times 10 to the 4th kilogram airliner with a kinetic energy of 1.1 times 10 to the 9th joules. So calculate the speed. All right, we're going to find the velocity. Again, they're using this interchangeably here, which probably isn't great practice, but the mass is 8 times 10 to the 4th kilograms, and the kinetic energy is 1.1 times 10 to the 9th joules. Our equation is KE equals 1/2 mv squared. So we want to solve for v. So let's get rid of the 2 on each side by multiplying, or the 1/2 by multiplying each side by 2. Let's get rid of the mass by dividing both sides by mass. And let's get rid of the exponent by taking the square root of both sides. So rewriting that a little bit neater, we get v equals the square root of 2ke over m. Right, and then I plug and chug. So 1.1 times 10 to the 9th joules over, times 2, by the way, over the mass of 8 times 10 to the 4th kilograms. So let's just go 1.1 times 10 to the 9th. That'd be seen. Times 2 equals, divided by 8 times 10 to the 4th equals, and then take the square root of that. So that's going to be 166. Oops. 166 meters per second. Let's look at number 3. 2 bullets have masses of 3 grams and 6 grams respectively. Both are fired with a speed of 40 meters per second. Which bullet has more kinetic energy, and what is the ratio of their kinetic energies? So I'm going to not do a lot of math on this one, but here's what I know. I know that here's bullet 1, and its kinetic energy is given by 1/2 mv squared. All right. Here's bullet 2. Its kinetic energy is given by 1/2 mv squared. I'll call this m1 and m2 v squared. Okay. Now, how does m2 relate? m2 is the same thing as m1, except it's twice as big. So if I rewrite this, it's 1/2 times 2 m1 v squared. Okay. It's 2 times the mass that this one has. Well, let me reduce this. That's the same thing as just m1 v squared, right? So the question is, what's the ratio, or which one has more kinetic energy? Well, this one does. This is m1 v squared. This was 1/2 m1 v squared. So this has twice as much kinetic energy. All right, and that's the ratio, 2 to to 1. All right, number 4. 2 3-gram bullets are fired with speeds of 40 meters per second and 80 meters per second, respectively. What are their kinetic energies? Which bullet has more kinetic energy, and what is the ratio of their kinetic energies? So this is a pretty good question. I'm not going to find the actual kinetic energies. I will say this, their masses, M1 is 0.003 kilograms and M2 is 0.006 kilograms. I'm sorry, no, that's not right. They both have the same mass. V1 is 40 and V2 is 80 meters per second. All right. What do I care about here? I care about which one has more kinetic energy. Well, the faster one has more kinetic energy. Okay, this is 1/2 mv1 squared. This is 1/2 mv2 squared. Okay, this one has twice the speed, so it's going faster. So it must. Everything else is the same. If v2 is bigger than v1, then this has to have more kinetic energy. What's their ratio? Well, let's say v2 again is 2 times v1. So I'm going to rewrite this as 1/2 m times 2v1 squared. Right? Now, if I reduce that, I get 1/2 m times 4v1 squared, because 2 gets squared as well. So 4 times 1/2 is 2, so I get 2mv1 squared. And this is 1/2 mv1 squared. So how does this relate to this? Well, the ratio of 2 to 1/2 is 4 to 1. This is a 4 or a 1 to 4 ratio, bullet 1 to bullet 2. Okay, kinetic energy. Doubling your speed gives you 4 times as much energy. All right, let's look at finally number 5. Turn over here. Okay, number 5 says a car has a kinetic energy of 4.32 times 10 to the 5th joules when traveling at a speed of 23 meters per second. What is its mass? Okay, well, KE equals 1/2 mv squared. If we solve for mass, we again want to get rid of 1/2, and we divide both sides by v squared. So I get m equals 2ke over v squared, and then plug and chug, 2 times 4.32 times 10 to the 5th joules over 23 meters per second squared. So 2 times 4.32 to the 5th. And then divide that by 23 squared equals 1633 meters per second. Sorry, kilograms, not meters per second. Finding the mass. Okay, moving on. Last one, page 162, numbers 1 through 4. And again, I won't do all of these, but number 1, a student wearing frictionless inline skates on a horizontal surface is pushed by a friend with a constant force of 45 newtons. Okay, so you got person on skates. Here's my person. Being pushed forward with a force of 45 newtons. That's F. How far must the student be pushed starting from rest so that her final kinetic energy is 352 joules? So there are 2 situations. There's the beginning and the end. All right, at the beginning, she has starting at rest, so V equals 0, that's V1. At the end, V2, we said that we don't know, but we want her kinetic energy to be 352 joules. And here, her kinetic energy is 0 because she has no velocity. So the question is, how far must the student be pushed? So D equals what? Starting from rest so that her final kinetic energy is 352. So this is a work kinetic energy theorem problem. So work equals final kinetic energy minus the initial kinetic energy. And if the final kinetic or initial kinetic energy is 0, you can cross that term off. Work is force times distance. Kinetic energy is we know that it's 352 joules. So how much force is there? 45 newtons. And we want to find the distance, so let's divide both sides by F. That becomes D equals 352 divided by 45. And that's 7.8 meters. All right, that's number 1. To number 2. A 2 times 10 to the third car accelerates from rest under the actions of 2 forces. One is a forward force of 1140. So here's my car. There's an 1140 Newton force to the right. The other is a 950 Newton resistance force due to friction. Use the work kinetic energy theorem to determine how far the car must travel for its speed to reach 2 meters per second. Okay, so we want two situations. V1 is 0, it starts at rest. V2 is going to be 2 meters per second. And the mass of the car is 2 times 10 to the third kilograms. And so we want to use the work kinetic energy theorem here. All right, well, what's our net force on the car? The net force on the car is going to be 1140 minus 950. That's going to be 140 plus 50, so that's 190 newtons. So that's the net force on the car here. That's the only force we really care about. Using the work kinetic energy theorem, work equals KE2 minus KE1, or K1, K2. I'll put the E's on there. Starts at rest, so there was no kinetic energy at the beginning. And this is going to be 1/2 mv2 squared. This is going to be force times distance. The question again was, how far does the car go? Divide both by F. D equals 1/2 times 2 times 10 to the third kilograms times 2 meters per second squared over 190 newtons. All right, so just a lot of calculating here. It's going to be 0.5 times 2 times 10 to the third times 4 equals 4,000 divided by 190 equals 21. So 21 meters is the answer for number 2. All right, and I'm going to just skip the last 2 because they are pretty similar. Number 4, the only difference is you're trying to find the net force. So you'll get to this position and you'll have distance. You'll just solve for F instead of solving for D. All right,